Hello, I am Jiyeok Park, a PhD student in the Programming Language Research Group at KAIST. In this presentation, we will introduce our technical research paper with the title JEST N+1-Version Differential Testing of both JavaScript Engines and Specification. We will first explain the motivation of this work and then explain the details of the research topic. In the beginning, JavaScript was designed for client-side programming in web browsers. However, nowadays, thanks to its good portability, we can use JavaScript in server-side or system programming and even in small embedded systems. Moreover, JavaScript is one of the most dominated programming languages in the world. According to the Octopus, which is the annual report of GitHub, JavaScript is the top-ranked programming language in GitHub repositories. To describe the syntax and semantics of this JavaScript, the ECMA Technical Committee 39, shortly TC39, maintains ECMAScript as its standard specification. Thus, existing JavaScript engines must conform to ECMAScript. Moreover, unlike the traditional waterfall model, sometimes JavaScript engines are updated first, and then the specification is updated later, with new language features introduced by engines. Thus, ECMAScript also must conform to existing JavaScript engines. Then how can we check the conformance between JavaScript specification and existing engines? The current approach is to manually define the JavaScript conformance test based on ECMAScript. Test 262 is the official conformance test suite written by TC39, and JavaScript engine developers check their engines using test 262 and their own tests. However, there are two critical problems in the current approach. First, TC39 manually writes test 262, thus it is labor intensive, and also we cannot guarantee that test 262 correctly represents the syntax and semantics described in ECMAScript. Moreover, there is no existing approach to check whether ECMAScript conforms to existing JavaScript engines. To alleviate this problem, we propose a new technique called N+1-Version Differential Testing. While the traditional differential testing utilizes only the cross-referencing oracle between multiple implementations, instead, our approach utilizes and tests not only implementations, but also their specification. Now, I will explain our approach with simple examples. We first automatically synthesize conformance tests directly from ECMAScript. Then we run them on multiple JavaScript engines. Assume that only V8 engine fails a test, then similar to the traditional differential testing, we can say that an engine bug exists in V8 related to the test. However, our approach becomes more interesting in this case. Assume that only Graalvm JavaScript engine passes a test, but the other engines do not. Then the test itself does not conform to most of existing JavaScript engines. Thus, we can say that the test might be wrong, and ECMAScript has a specification bug related to the test. Moreover, we can say that Graalvm JavaScript engine also has an engine bug because it passes the test which should be failed. To actualize N+1-version differential testing for JavaScript, we developed a tool named JEST, a JavaScript engines and specification tester, and this is its overall structure. JEST utilizes another tool named JSet, which extracts a mechanized specification directly from ECMAScript. Thanks to JSet, we can mechanically handle syntax and semantics described in ECMAScript, even though it is written in English. Using the extracted mechanized specification, test the synthesizer, synthesizes conformance tests. Then, JEST detects engine and specification bugs by running the synthesized tests on multiple JavaScript engines, and Bug Localizer localizes detected bugs based on test results with a spectrum-based virtual localization technique. Now, I will explain the detail of test synthesizer. Test synthesizer consists of four submodules parametric with the extracted mechanized specification. First, the seed generator utilizes the language syntax to generate seed JavaScript programs as the initial program pool, and target selector selects a single target program in the program pool guided by semantics coverage. Then, using five different mutation methods, program mutator tries to construct a new mutated program that increases the semantics coverage and adds it to the program pool. Target selector repeats this process until the semantics coverage converges. Finally, assertion injector modifies the programs in the pool to generate conformance tests by injecting appropriate assertions reflecting the semantics described in the extracted mechanized specification. We evaluated JEST with the latest version of ECMAScript and four different JavaScript engines. The latest ECMAScript version is the 11th version called ECMAScript 2020 or shortly ES11. And we selected these four JavaScript engines as our targets because all of them support all JavaScript language features in ES11. So ES11 and these JavaScript engines must conform to each other. We first measure the syntax and semantics coverage by 1700s tests synthesized by JEST in 100 hours. They have almost 98% of syntax coverage and 87% and 78% of semantics coverage for statements and branches in abstract algorithms respectively. These two figures describe how the semantics coverage changes during the test synthesis. It shows that the conformance tests synthesized by JEST have similar semantics coverage compared to test 262, and the coverage slightly increases after fixing specification bugs in ECMAScript. From four JavaScript engines, JEST detected 44 bugs, and this table presents how many bugs are detected by each kind of assertions and for each engine. Among them, I will introduce two interesting bugs. The first engine bug is related to this program. According to ECMAScript, the expected behavior of the program is throwing a reference error for the variable x. However, QuickJS engine normally terminates this program without any exceptions because it initializes the variable x with undefined in this object destructuring pattern for parameters. Another engine bug is related to this program. According to ECMAScript, this program must terminate normally. However, GraalVM JavaScript engine crashes with an internal error. It is a critical bug because the engine unexpectedly dies and we cannot even catch it by the try statement. Moreover, JEST also successfully detected 27 specification bugs in ES11. Most of them were already reported and fixed by other contributors in the official ECMAScript repository. However, one specification bug related to the semantics of property definitions was never reported before. Thus, we fixed and reported this bug like this, and it is confirmed by TC39. Among 71 engine and specification bugs, 64 bugs are semantics bugs. Using SBFL technique, we localize them on the semantics of ES11. This figure shows the ranks of algorithms that cause the semantics bugs, and the average rank is 3.19. It means that conformance tests synthesized by JEST also have a high accuracy of bug localization. To conclude, we presented a new technique called N+1-Version Differential testing to check the conformance between multiple implementations and their specification. We developed JEST to actualize this technique for JavaScript. Our tool successfully synthesized 1700 JavaScript conformance tests and successfully detected 44 bugs in existing JavaScript engines and 27 bugs in the latest version of ECMAScript using the synthesized test. We believe that our approach is also applicable to other fields having a well-written specification. This is the end of my talk. Thank you for listening.
Okay, hello everyone. Welcome to this afternoon's question and answer session. Well, afternoon in CET Europe at least. Hello to all of you from anywhere on Earth. So by the round of applauses, it seems that Gioc's presentation was very interesting for the public here today. For following the session. So at this point, I would like to welcome Gioc Park. He's from KAIST University, who has illustrated the work and the paper that he has done. If anybody has questions, please type in the chat, and I will ask the questions to our author. So, in the meantime, that you guys write up some questions, I would like to ask you a question, Gioc. So, here we have a question. I'll ask Na Meng is asking a question. So she would like to know, how do you compare JEST with existing differential testing for JS compilers, such as, for example, automated conformance testing for JavaScript engines via deep compiler fuzzing?
Yeah, so yeah, I know that papers. I think this paper is published in PLDI this year. So I think our paper is first, and then that paper is parallelly studied about two different sides. So yeah, so I think it is impossible to directly compare with that paper, but during our research, there is no existing paper about the differential testing for existing JavaScript engines. So there's no comparable existing tools or the kind of literature papers. So we just compare our synthesized tests with the official conformance test called test262 maintained by TC39. So yeah, so this is my answer for the comparison with. Yeah.
Okay, so thank you. And so Na is also asking another question. So she asks if you have conducted any experiment to compare JEST with the existing tools. So, like, I'm assuming she's asking if you have compared JEST with existing tools in testing and in experimenting it.
Yeah, so to the best of my knowledge, there is no existing differential. Again, there is no differential testing tool for JavaScript engine for the in the sense of generating the conformance test. But yet now there is a new paper in PLDA 21. So in this year, so I think we can compare with that paper with our approach. Yeah. So yeah, this is my answer.
Okay. Thank you, Gioc, for your answer. So I will go on with my question, I guess. So in terms of the evaluation that you carried out with your tool, you have selected 4 JavaScript engines.
Yeah.
So based on what criteria or what selection criteria, why did you choose those engines and not other ones?
Yeah, so there are other major JavaScript engines, for example, the other in some web browsers. So, but we only selected these 4 because only these 4 major engines fully support the modern JavaScript engine features, even presented in the recent version of ECMAScript. So, for example, another JavaScript engine for Safari is not supported the new language features presented in this or the last year. So only we selected this for JavaScript engine because of that criteria. Yeah.
Okay. And so you guys have in your paper, you propose JEST tool, right? So
Right.
I'm wondering, how do you think the results of your research can be beneficial for like a software company? Why should like developers or software companies adopt or use what you are proposing? What are the benefits?
So you mean the software, so you mean engine developers or the kinds
Yeah.
of people? Yeah.
Yeah.
Yeah. So I
Like
think,
not researchers. I mean, what are the benefits
yeah,
to the practitioners, let's say?
practitioners. Yeah. So especially for specifically engine developers, because it's highly related to our work. So yeah, so I think this is the first work to utilize the ECMAScript, directly use the JavaScript specification ECMAScript. So their implementation, existing JavaScript engines must conform to ECMAScript, but there is no existing tool to automatically mechanically handle the ECMAScript. But now we can have our tool to automatically synthesize directly from ECMAScript, directly conforms to ECMAScript, and now we can test the new features automatically synthesize this test. So I think, yeah, the tool is uh, directly helpful for that engine developers to test their engines. So by synthesizing more tests using our tool, and after new features introduced in a new version of ECMAScript, I think.
Thanks. So when you say that you have this tool and the engineers can, especially developers can especially use it, do you see any limitations in tool, like in its adoption, in terms of whoever's going to use it? What are the
So
limitations either of your study? What are the limitations of your study?
limitation. So yeah, so I think our current limitation of our tool is so that so we used 5 different mutation algorithms for to generate more diverse JavaScript programs in our tool. But these 5 mutation techniques is not advanced. So I think it is kind of limitation of our current limitation. But I think for future work we can advance our tool to support more advanced mutation techniques to synthesize and covers more semantics. Uh, yeah, yeah,
So we have a question from Yunho. So he's asking if the approach is extensible to languages like C or C++ and their compilers, and if so, what is the expected obstacle? I don't know if this is one of the future works that you were looking into that you mentioned at the end of your paper.
yeah. So yeah, I think I believe that our technique is applicable for other program languages, not only languages, but also other software having well-written specification and multiple implementations. But yeah, so for example, C and C++ specification is also well written, but JavaScript specification is highly structured and well written, and so uh, make we can develop a tool to directly extract the mechanized specification from ECMAScript. But I don't know. I think the current version of specification for C and C++ is not enough to directly perform the this approach. So I think if some more advanced and well structured specification of C or C++ is presented in the future, then I think we can apply our approach for C or C++ or other various modern programming languages. Yeah.
Okay, so thank you for your answer. Thank you everyone for your participation. At this point, the backstage Q&A part is finished, and you can continue the discussion in the discussion room with Kiyog. And bye bye.